So thank you very much for the introduction. Thank you for the opportunity to show some things here. What I would like to talk about is approximating robust methods. So what we're trying to do is get faster methods to compute free energies, but not giving up the robustness of methods that are based in statistical mechanics. So the aim is to maintain the accuracy, but then we want to still use some speed up that we can learn from other methods. And I'll talk about two aspects there. I'll talk about a combination of methods that are typically seen as more approximate, but then we take the aspects that we like best of them and we combine them into one approach. And then I'll also talk a little bit about how we try to actually approximate a full thermodynamic integration curve from just a few simulations. So let me start with the first part. As I mentioned, there are methods that are typically considered to be more approximate in nature, maybe, and one of them that we've been working on for a lot already in the last couple of years is one-step perturbations, where we're basically simulating a non-physical reference state that shows overlap with some real end states, and we in one go try to calculate the free energy of going from our unphysical reference state to the real states. We do it in solution, we do it in a protein, and then you can predict ligand binding or relative binding free energies from those, basically. Now, what's the good things of this method? It's very efficient. You do only one simulation in principle, and the post-processing is recalculating a couple of atoms, so this goes very, very quickly, and it works very good, except if you do charges. So it works very nicely for small neutral groups. If you just do a methyl group somewhere, or you add a small neutral changes. It doesn't work so well for charged molecules. It doesn't work so well for things that have big dipoles. On the other hand, another approach of calculating free energies very efficiently is empirical end-state methods, where one of them is based on the linear response approximation, or LIE, for instance. And what you do there is you approximate the free energy by looking at the energy of the interaction energy, the electrostatic energies of your molecule and its surroundings. And then you would, in principle, if you want to do it correctly, you would need to simulate it in the state where it's charged and where it is neutral. Now, this works very well for electrostatics. That is derived also from it works in LIE or LRA approximations. People then tend to say, well, let's do the same for the van der Waals, and they approximate that as well. But that doesn't work so well. So what we see here is that we have two opposite methods that work well for different parts, basically. So that a couple of years ago already led us to suggest that we can maybe combine these approaches, where we say, well, what happens if we simulate an unphysical reference state? We use the one-step perturbation to calculate the free energy of going from my unphysical reference states to real molecules A, B, C, and up to Z. And then I use a linear response approximation to do the charging. That way I would only need to simulate basically these states that are drawn there. So instead of doing an alchemical process with a big change, where I'd have all these intermediate lambda steps, I would need much fewer simulations to do that. So the first thing we did that on was a toy system. It was a bit of an increased buckyball with different functional groups here, and then we had 4 different molecules in it. I don't want to go too much into the details of that here. It's just that we had 16 complexes, so we compared this with thermodynamic integration to calculate the absolute binding free energy for these 16 different complexes. And you see exactly what I was just suggesting, basically, that the free energy of the cavity formation, so the non-polar part, works best. So this is the deviation with respect to the TI. This is the average deviation with respect to the TI data. The one-step perturbation works much better than an ad hoc linear response or LIE kind of approach. And for the charging, it's the opposite. I didn't even put the number for the one-step perturbation because it was really far off, but you can see it here also. It's for the complete thing, 122 kilojoules per mole off, so that's a big deviation. But that linear response approximation works much better with, in this case, 10 kilojoules per mole. It's a huge scale that I'm looking at here because I have charged particles. And in the end, you can get for these 16 complexes a correlation with the TI and our linear, in this case, linear interaction energies combined with the one-step perturbation that is quite decent. Now that was just a model system, so then we moved on to a more realistic case where we did it in trypsin. So we have a series of compounds that bind to trypsin, and we have just different functional groups here. And first we did them all with thermodynamic integration, so we do the free energy change between the molecules in solution and in the protein. First thing that we look at is whether we get cycle closure. So if you have these various arrows, they should add up to 0. Now this is well, a couple of, or 1.5 kilojoules per mole basically, so that works quite nicely. And then we started to look at these individual aspects. And then the first thing that I want to mention here is this charging thing. So what we are doing here is we take the molecule, and the functional group that we're changing is actually completely neutral, and we're putting on the charges, yeah, from this. And so we can do that with TI, and it always works very well because you get roughly a straight line, and you need only a few lambda points in principle. But you get roughly a straight line. You don't get exactly a straight line. So that's exactly what you would be doing if you're thinking of doing, if you parameterize your Hamiltonian like this. So you have Hamiltonian as a function of lambda that is just a linear combination of the neutral and the charged state. Then it turns out that your derivative with respect to lambda is the electrostatic ligand surrounding energies. So that's easy to get. And now if you actually try to do that with this LIE method, which is assuming that the neutral state we don't need to simulate, because we are only doing half the molecule, this works really badly here. So then you would approximate the red curve to the blue one, very bad. If you do linear response, where you would say I also simulate the neutral state, so that would be more appropriate, you get this straight line, because it's basically the average of these two. Beta is half, so you get the average of those two. That's basically the straight line. So you're getting there, but you're not really so precise yet. So then what we suggested, or this has actually been suggested in the late 90s already, where people were doing free energy extrapolation. We don't only know the derivative of the free energy with respect to lambda, but also its second derivative. And the second derivative, if you have this parameterization of the Hamiltonian, turns out to be just the fluctuations of this energy term. And in the 90s, when they tried this, the simulations were too short that these things didn't converge. But nowadays we can do, then you did 100 picoseconds maybe. Now we do a couple of nanoseconds, and these fluctuations actually converge as well. That means that we don't only know the point here, but we also know the slope of the DHT lambda curve already. So what we then do is we say, okay, we still simulate only the end states. We know where it should go through at the neutral and the charged state. We know the slope, and then we just fit a third order polynomial to those four data points basically that we can measure, and then we integrate that one. So we approximate the TI curve just from those two simulations by looking at the fluctuations and the values themselves. If we now combine this with the one-step perturbation approach, then you can see that our for the non-polar part, the one-step perturbation works very nicely as well. That's just comparing the TI to a TI again. And these are the deviations with respect to the TI if you do the charging free energy, and you see this third power fitting indeed is much superior to the other more approximate methods. And then what you are getting from it, if you do the one-step perturbation with the third power fitting, you get deviations with respect to the TI that are a little bit bigger, but they're in the order of 3 kilojoules per mole, 4 kilojoules per mole for the total delta G. So that's a very quick estimate basically, because now here we did a simulation, total simulation time of 58 nanoseconds, and that would need to be compared to the 245 nanoseconds that we did for the TI basically, so that if you would do every step individually with the TI. You can even approximate this state. You don't really need to simulate this state. You can even approximate that one from this simulation as well. Then it speeds up a little bit more, but you also lose a little bit more in terms of the precision. Now we said we should do this in a more systematic way, basically. So this was one example. We were very happy that it works. And then we said, okay, we need to do this more systematically. So what we are now looking at is first for solvation free energy, and then we also do it in peptides of all the side chains. So we first take the small molecules, which is we take all the analogs of the side chain. So we cut them between C alpha and C beta, and we look at the solvation free energy of the small molecule that you end up with. And then we'll later on, but then the next stage we also do it in a small peptide, and then of course also in a protein. That's very nice, because what you can then think of is that you can get the free energy differences between all amino acids at a certain position. So you can basically do a computational saturation mutagenesis from just a few simulations. You would simulate the reference state, you would simulate the real molecules that you're anyway interested in, and you would be able to get the free energy differences between them in a robust way. So first the electrostatic part. Basically we see the same, just the way that we do it now is charged to neutral, so the curve looks the other way. But basically it's the same as we saw before. The TI doesn't give a completely straight line, but if we approximate it with the third power fitting, we get a very decent approximation. In some cases it doesn't go all the way to exactly the same slope. So for in this case for methanol, for serine in water, or the serine side chain in water, which is just methanol. We still have a bit of a deviation, but it's clear that the third power fitting is usually a better approximation. Then if we combine this again with the one-step perturbation, we need, of course, the amino acids are different sizes. So what is our reference state now? We tried two things. One where we just have a single soft core sphere. I didn't go too much into the detail of what we do there as a reference state yet. It's a soft core sphere. That means it is a particle that can sometimes have overlap with the surrounding atoms. So there's atoms that approach it, they bump into it in principle, there is a repulsion, but if they have enough energy, they can actually fly through. So we just use the soft core potential of the that people are using in free energy at the time. When we use two of those reference states, either one sphere, but then of course obviously something like an arginine side chain or tryptophan will not fit in it. So we also have a double sphere system, and then we align our molecules to it, and we actually sample a little bit their conformations in within the sphere when we calculate the energies. That's more of a detail. Now the resolution is not very good, but what you see here is again, the comparison against the experimental solvation free energy. So we have experimental solvation free energies for our molecules, we have the calculated values, and then we can do this for TI, that's the blue circles, and we can do it with this OSP third power fitting method. The deviation from the line in the case of the TI is 1.5 kilojoules per mole, which is absolutely no surprise because this force field was parameterized to get these values, so this is just what we put in. But the agreement with the third power fitting, a more approximate method, is still very decent with 3 and 3.1 kilojoules per mole, and also with respect to each other, they're about 2.3 kilojoules per mole apart. I have here more compounds because I did not put in the charged ones there. Good, so then we wanted to do this also in a tripeptide. So as a first test of whether we can do this in a protein. So what we now have is this is our reference state. We put our soft core particle, this R atom, at a little distance with the dummy atom so that it actually samples a little bit more conformations. And what we do is we put in our real molecules, but the neutral ones, and we put in different conformations. So if we now want to calculate the free energy of in this case, the arginine, we have first generated our own, according to our force field, a small conformational library, but you can also just take a Rothermer library in principle. And we put different conformations of this in the simulation afterwards. So we simulate the weird reference state. Afterwards, we put in these 5 conformations, calculate what the free energy for each of the conformations would be. We know the balance between the conformations from the Rothermer library, and we can combine that all into a free energy for the neutral state. And then we simulate this one and we simulate that one, and with the third power fitting we calculate the charging. So basically for one amino acid it's these 2 simulations and one reference state simulation for all of them together. That means that for 20 amino acids you're done with 41 simulations basically to get the free energies between all of them. Now how well does that work? So again here I compare to TI, so I have the TI data on the y-axis here, and on the x-axis our simulated data, and you see that that the correlation is really very good, 3.8 kilojoules per mole. So also when we need to take a conformational sampling of the side chains really into account, we can have quite a robust approximation of the molecules. There's here isoleucine. This is just a zoom. Isoleucine is still a bit challenging for that case. Now, so this was the first example that I wanted to show where we're trying to get the real free energies from just a few simulations and approximate them. So we are combining the strength of various efficient free energy methods. We have the non-polar contributions from the one-step perturbation and the electrostatic contributions from the end-state methods, basically. Now the third power fitting is a parameter-free approach, so that's nice. So things like LAE or LRA are often used by fitting the alpha-beta parameters. There's no empirical fitting necessary here. And it comes at no additional cost because we just include fluctuation data rather than only the average value of the energies. But, of course, there's no reason why the curve has to be a third-order polynomial. That's just given by the fact that then we have 4 unknowns and we have 4 knowns, basically, so we just leave it. And then we were wondering if we cannot predict the TI curves directly. Can we not do this in a more elegant way, maybe completely? So what we're then trying to do, we're trying to look at the TI curve itself. So now I have a bit of a weird notation. but that's just, it becomes, later on it becomes internally clear. So what I use here is a big lambda for my reaction coordinate, and this is what we do in TI. We have our ensemble average at a given value of lambda, and we integrate over it. Yeah? So this is what we saw before. Now if you start to do a simulation with TI, what you could do is you could just say, okay, I first simulate just 2 points, and then we get very similar as before, we get a straight line. Yeah? That's not a good approximation. Then we do 3 points, we get more of a curve already, 4 points, 5 points, 6 points, and then when we start to do 11 points, all of a sudden, at 11 points we start seeing a peak, and with 21 points we see more of a peak, so you always have to make sure that you don't miss the peaks. Basically, if you start adding points to your simulation, did you miss the peaks? And what you need to have for the TI is a smooth curve that you want to integrate. So you would want to get something like this. So here we did 101 points. This is the solvation of methanol in water. And now what we were wondering is if we could not already predict the shape of the curve from just a few simulations in the beginning. So what we would want to have is that we could do 6 simulations. So we simulate a few. This would be a lousy prediction basically, because integrating this red curve would be very would not give us the correct answer. But can we, from the simulations that we have, predict already where the curve will be? So can we make the predictions from the simulations that we have to find out where these peaks are, and can we suggest where the curve is? Now, give it away already, we can. This is a predicted curve, so the green one is now the predicted curve from these 6 simulations that we can approximate the black curve basically from the simulations. Now, how do we do that? It's actually not super fancy or magical. The thing is that we need to predict what the derivatives will be at different lambda values. Now that's always difficult if you use soft core. So this typical shape that I now showed is one that you get if you do soft core. But we then just decided let's compute those during or on the fly, because that's not super expensive. This is not a very difficult thing to do. So what we're writing, our energy is 1 minus lambda can be to the power n. And now here I use different kinds of lambdas, one for the scaling and one for the softness. Doesn't really matter so much. But I just monitor this thing for the softness Lennard-Jones lambda, and I monitor it for state B for the softness Lennard-Jones. And in the derivative, I need a similar term, that these 2 terms are the same, but I also need their derivatives, basically. And now what we do during the simulation, we already calculate these sums for 101 lambda values. Yeah? So we just do that extra. Now that sounds very expensive because you do 101 energy calculations extra, but it doesn't cost you so much, because typically you have a simulation of 50,000 atoms and you're doing 10 perturbed atoms. You only need to do this for the perturbed atoms. So it's basically 100 times 10 atoms. That's 1,000, as if you have 1,000 atoms more. So you need to do a few calculations more, but we store these summed properties, and that allows us to reconstruct the energy and its derivative at any lambda point from the simulation. Then we're not there yet, because you still need to account for the fact that you have a different sampling, of course. So we just do the reweighting. So what we do is we construct the Hamiltonian at any predicted lambda value, and then we get the energies, we get the derivatives, we do an umbrella sampling reweighting, and then we get to the true value, basically. Now, how does that work? This is the prediction from one simulation. From lambda 0 you get the red one, from lambda 1 you get the other one. If you would combine them, we can combine them with a linear weighting scheme. If you combine them, you already get a decent curve that looks actually not so bad, just from the 2 simulations at the end. And then we can do different kinds of predictions if we do that. So if we simulate it every 0.1, we get the red one. Now you can not distinguish it from the real red one, from the real black one. But already the blue one, where you simulated basically 4 points, you get a very decent prediction of your full TI curve from just the 4 simulations that you did. Also here, in view of time, I will go very quickly through this one. Also here we did it for this benzamidine case. Of course in the protein the sampling is a little bit more difficult, but still we can predict the black curve with our reference TI data from having 6 simulated values very decently. I have also some tables where I can show this in numbers how well our curves deviate from each other, but I hope that you believe it just from how much the curves look like each other. So what are we doing? We're trying to reduce the number of unphysical simulations that we need to do, so the intermediate states of the thermodynamic integration, or get rid of them completely. If we do the one-step perturbation third power fitting approaches, then we're basically really focusing more on simulating our physical states. or in the extended TI, we're using exact statistical mechanics to predict where the TI curve will be. Now, what are we doing this on? We're now applying this in true protein environments. And another teaser a bit is that the extended TI machinery we can also use to optimize actually the shape of the curve. You can do a few simulations, predict where the curve is, then you know where to simulate. That can be useful already. Or you can also predict if a different lambda parameterization would lead to a flatter curve. So you can actually predict already whether you can come up with a more efficient path to get a flatter curve, which is nicer to integrate. With that, I stop. I acknowledge some people, some group members, some funding and collaborators, and I thank you for your attention.